So hopefully you guys have been watching this as entertainment while you were waiting. This is actually called a water bridge, or a floating water bridge. It's actually water that's going from two beakers from one to another, and the way they do this is they put some sort of electrical charge on the water, and it actually flows from one side to the other. And it turns out that they don't exactly understand exactly why it does this. But they have some ideas, of course. They're always full of ideas. So how do I get out? Escape? X. This one? Okay. Never used this before, so. That's okay. Just as long as I can see. Okay, so like I said, what we were just looking at, it was called a floating water bridge. It's actually an active area of research right now that scientists are actually trying to study it right now to try to understand why it works. They don't exactly know why, but they have lots of theories. But they do know that it only happens with certain liquids, very few liquids actually, and one of them is water. And the only liquids that will do it is a liquid that exhibits what's called hydrogen bonding, which we'll get to in a little while. I was going to make the title of this talk Wacky Water, because there's so many strange things I found out about water since I started studying this. But I said that to my wife, and she said it sounded like an amusement park ride, so she said something a little more sensible, so I called it Uniquely Designed, Water Uniquely Designed. So. Okay, so tonight we are going to talk about the unique properties of water, then just some of the unique properties of water. It turns out there's quite a few of them, and there's definitely not enough time for me to go through all of them. We're going to get to the molecular level of water. I even brought my little molecular model of water here, so we can use that as a exhibit a little bit later, learn a little bit about it. And then we're going to talk about the philosophical implications of what we've learned. My goal tonight is to make a case that water is uniquely designed by an intelligent creator with the purpose of supporting life. So, and then at the end we'll have some questions. I'll take questions and we can have a discussion or what have you. Okay, so just some water basics here. The human body is 60 to 70% water. You probably heard that before. It turns out that if you are a living organism anywhere on this planet, you probably are composed of at least 50% water. So it's not just humans, it's any living organism, plants, animals, what have you. So it's the third most abundant molecule in the universe. It turns out that, depending on where you read, sometimes they say it's the second most abundant molecule in the universe. That's because the first molecule, the most abundant molecule is hydrogen, and there's actually two forms of hydrogen, so depending on how you count it, it's the third most abundant molecule in the universe. So anyway, so it plays a greater role in living processes than any other molecule. Michael Denton, he's a molecular geneticist, says, if the vital activities of the cell are the movements of pieces on a chessboard, then water would be the board. Life just needs it. Some people would argue that the only reason water is so vital to life is because that's how life evolved. If we had oceans of sulfuric acid or ammonia, then life would have evolved around sulfuric acid or ammonia. But I hope that once you see how unique water is and how much it appears to be designed to help life along, that By the time you leave tonight, you'll be convinced that that's not the case. So the way I want to do this is for you to think of yourself as a designer or an engineer. It's easy for me because I'm an engineer, but think of yourself as a designer and think about what it takes to make a good design. So let's take a look at our first unique property of water. Okay, so the first property of water is that it's a universal solvent, is the word that I've heard used a lot. What that means is that it has this tremendous ability to dissolve other solvents, or dissolve other substances, sorry. Water can dissolve more substances in greater quantity than any other liquid. And why, actually liquid or gas, actually. So why is this important? Well, there's lots of reasons. Here's a couple. One is erosion. If water couldn't dissolve things, then it wouldn't erode things as well. And water picks up minerals and salts and things and transports them throughout the world. If it didn't do that, then when we drink our water, we wouldn't be getting what we need to live on. It turns out the world's rivers collectively transport 5 billion tons of dissolved mineral matter per year. We need those salts and minerals to live. Okay, another reason why it being a solvent, this universal solvent is a good thing, is your circulatory system. Well, you have blood, right? Well, blood plasma is 50% water, and it uses water to dissolve all the nutrients. So even though you get the rivers that take it, they put it in a bottle, whatever. If you can't, once you drink it, you got to have something that transports it around your body. Well, blood plasma is 50% water, and so it can dissolve all that stuff and transport it to different parts of your body. And just to give you an idea, I found this on a website that scientists have actually studied seawater and tried to figure out what kinds of things can be dissolved in seawater. This is just the elements. See the periodic table of elements over there. There's 76 elements that can actually be dissolved in water. So think if you wanted to build something, like a car or a house, the more different types of materials that you have available, the easier your job's going to be. So once again, I'm kind of going back to if you wanted to be a designer. I used to do proposals for designs for the government, and one of the things that I had to do was to justify the medium that I chose for the design. So if I were given the task of designing life, I'd choose a chemical that can give me the most pieces to build with. So I'd choose water. So. Okay, so one of the things we need to talk about is why is this life so dependent on a liquid and not, say, a gas or a solid? That's going to become a little more important a little later on in my talk. But we have to kind of get some basics covered first before we move on. So think of yourself as a designer. You need a medium to transport the minerals. We immediately think of a liquid, but is that because we're biased? Because our living life on Earth is based on water. Are we biased because of that, or is it actually liquid actually the best medium? So remember, you want. So it could be. You got to think in terms of could it be a gas, a liquid, or a solid? It turns out that a solid won't work because, there's what? I don't know what my notes meant there. But you have to have something that can move, and solids don't move too well. Nothing like, you can't have a river of solids. Gas won't work because, the wind can't carry enough minerals around. It's not practical. So we're kind of stuck with a liquid. Remember, you want one medium that can take the minerals out of the earth, distribute it throughout the world, but also you want the same medium to work within the organism that you're designing for cellular processes. Solid is too rigid to allow molecules to come in contact with each other, and gases are too volatile and easily altered. So, I want to go to the next thing here. So, one more here. Cellular processes and liquid medium. So the conclusion is liquid medium is required for life. Sometimes we take for granted that water is liquid at normal temperatures. Water is liquid from 32 degrees to 212 degrees. So sometimes you take that for granted, but it turns out that water is the only common inorganic liquid found on Earth. You could argue that there are other substances that would be candidates for the medium for life, but you'd have to raise or lower the temperature range because that's the water is the only chemical that's actually liquid at what we call room temperature. So you could say, well, maybe you could have on another planet, it could be a lot colder. So maybe a lot colder, you could have liquid, some liquid down there, really a lot hotter or something. But the problem is that, let's see here, most chemical processes required for life require temperatures in the range where water is liquid. Outside this range, you get all sorts of problems. So as biochemist Fuzz Rana from Reasons to Believe says, water's liquid temperature range is ideal. You need it to be high enough for molecular mobility, but low enough to prevent instability. So if you're going to design a medium for life, you'd want it to be liquid at normal temperatures. Water is the only common inorganic liquid. Okay, so the next unique property of water we're going to talk about is what I call ice floats. We don't usually think about this, but when you put an ice cube in your water, it floats. There's not very many liquids that do that. It's actually almost unique to water. This is a graph here where this is temperature down here. I've kind of cut off a little bit of it here for a minute. This is in centigrade, so this is 212 degrees Fahrenheit, and this is at 32, and this is the density. So as things get colder, as things get colder, things usually get more dense. So you've heard hot air rises, cold air sinks. So that's the normal way things normally work. Well, that's how water works too when it's liquid. But as soon as it goes solid, something amazing happens. All of a sudden, the density drops. It gets lighter than the liquid. And then it kind of, at other temperatures, it's about the same. It gets a little bit, it kind of follows a normal trend. But when there's this phase change that happens with water that doesn't happen the same way with other liquids. The only other liquids that we know of that actually do that is molten silica, a compound of glass, and some metals like gallium and plutonium. So get a little jar of plutonium, I suppose you can get a little cube of plutonium and put it in and float on top, I guess. Okay, so what? Ice floats. Who cares, right? Well, there's something very strange that happens here. Ice floats, it helps explain some strange things we see, and here's one. Okay, this really happens. Hot water can freeze faster than cold water. I actually tried it. It didn't work for me. It turns out, after I did a little more research, you have to have just the right temperature of hot water, just the right temperature of cold water. Then you have to have a really good freezer that's uniform throughout. And there's all sorts of things you got to do that I wasn't willing to go through. But let me just kind of show you what can happen here. Let's see here. It's called the Mpemba effect because it was discovered or described, I guess, by some scientist. I think he's still alive, actually. It's not like I think they actually knew this before. I think that the Greeks actually talked about this a little bit even. But anyway, he got it named after him. It's actually not even fully understood. However, let's see, what was the name of it? The Royal Society of Chemistry in England, I assume, offered a contest for people to submit papers to explain this, and they offered some reward for whoever came up with the best paper. Well, I actually read the paper. It wasn't very long. It was a lot of I don't knows in it, but he actually does go through what different people suggest is the solution to it and all this. But here is one of his explanations, just to give you an idea that it doesn't make a lot of sense that hot water could freeze faster than cold water. By the way, has anybody ever heard that before? Yeah, I had heard that before too. When I was in college, a family that I stayed with was trying to convince me of that. Because they would tell me they're going to put the ice cubes in the freezer, and they said, well, put hot water in there so it will freeze faster. I thought, you're stupid. I didn't say that. I thought it was really silly. So here's an explanation. Actually, this is true, but what we don't know is if this is the primary effect or not that causes this, okay? So you put the hot and the cold water in the freezer, and what's going to happen? Well, the outside air is colder than what's inside, right? It's a freezer. So the outside of the glass is going to freeze first, okay? Okay, then what happens? Well, look at what happens at the bottom of the hot water. It's hot water, so what does hot water do to ice? Well, it melts it. So all of a sudden it's going to start floating up, okay? Well, after it starts floating up, what's going to happen? It's going to form a layer up on top, okay? Well, as it floated up, it actually went through the cooler water. I mean, it's hot water, but it went through it and actually cooled it down. Whereas the cold water doesn't do that, okay? So what happens in the end is the hot water actually can freeze faster than the cold water because of this circulation. Now, it doesn't just happen to the bottom. It can also happen to the sides and such, okay? So that's one simple explanation. They have some more complicated explanations, which I don't understand, which involve supercooling and all these techie things. So I like this one because it was actually in this paper that actually won. The person who actually won the award actually had this to say. He said, once again, this small, simple molecule amazes and intrigues us with its magic. Now we got scientists talking about magic. So.
Are we allowed to ask questions during, or should we wait till the end?
If you want an explanation of this more, sure, go ahead.
I was just going to say, like, I've seen YouTube videos of people inside the area tossing like a bucket of water into the air, and it like freezes and like falls down almost like snow.
Yeah. You can actually do that with a. I've seen it with these super soakers. You can take a super soaker and get it. I forget how you do it, but you put it under pressure or something, and you do it. And you do it when it's really cold out, and it goes out and makes all these ice crystals and stuff. I know exactly hot water freezes. Okay, yeah, so gotta start off. Yeah.
Sorry.
I mean, yeah. Okay, so that's all well and good, but who cares? I mean, it's a great little magic trick, if you want to call it, but doesn't really say too much about life. So, what if ice did not float? Let's talk about something a little more real. Okay, this is my drawing of a lake, okay? Use your imagination. Okay, we're looking at the side view, so this is the top of the lake, this is the bottom of the lake, okay? These are the sides, okay? All right, so what happens? Well, when it gets cold in the wintertime, maybe not here, but where I'm from in New York State, when it gets cold in the wintertime, ice, things start to ice up, right? Well, if ice didn't float, what's going to happen? The ice is going to be at the bottom of the lake, okay? All right, the sun comes out, warms it up a little bit. Well, it doesn't reach down to the ice at the bottom. So what happens next winter? Ice, more ice, gets colder. What happens next winter? Ice colder. Well, what happens is that eventually the lake freezes over except for the very top of the lake. So any place on Earth where there's lakes that have a winter, they would all be frozen over. So no little fishies swimming around down here anymore. Okay? So not only do you not have little fishies swimming around, but there's all sorts of other things that, we use lakes for all sorts of things. So that's one major effect of ice floating. So if we didn't have oceans of ice, if we had oceans of something else, like ammonia or something, and it was the temperature range that ammonia was liquid and all that, eventually you could get into that kind of a problem. Okay. So, but ice does float, right? Everybody knows that. Okay, so what? Here's my lake again. If I guess what's going to happen, the ice is floating at the top. Sun comes out. What happens? Ice melts. Sun goes away. Ice comes back. Only the surface freezes. Okay. So because ice expands when it freezes, water gets. There's other things that happen too besides just this. Water gets into cracks of rocks. And then when it freezes, it helps break up the rock. Well, erosion is very important to life, so that's another important thing. It breaks up the rocks, it adds to erosion. There's also something called lake turnover that makes it so that the yucky stuff on the bottom actually comes to the top and such. Well, that has to do with ice being, water, the strange temperature fluctuations in the water. It's almost unique to water, like I said before. So, like I said, molten silica. Well, we have molten silica lakes, I suppose. Okay, so let's talk about another unique feature of water. Heat capacity. Okay, so we're going to get into some thermal things, so it's a little bit boring, but bear with me, okay? Heat capacity is the measure of a substance's ability to absorb heat, okay? So, here's the Earth. It's got water in it. When the sun shines on it, it heats up, but depending on how much heat you put into it, or sorry, how much heat goes into it, the temperature's going to rise, right? Well, water is such, heat capacity has to do with how much it can absorb before it actually raises, its temperature raises, or rises, whatever. Yeah. So anyway, so you want it to be high, you want this heat capacity to be high because it'll even out the day versus night temperature. It's really important that we don't have really strong changes in temperature on our planet. Because the more drastic changes you have, the more difficult it is to do your design for your life. Because you got to make it compatible with really cold temperatures, really hot temperature. That's a much more difficult problem to design. Okay, I'm trying to think from a designer's point of view. We used to have to design circuits, and one of the things was what's the temperature range it has to work at. You probably know this too, right? The government was usually the worst because they needed it to work in Antarctica and they needed to work in the Sahara Desert, you know, all that kind of stuff. So anyway, so you want it to be high. So what I did was I just drew a little shady side of the Earth there, so you can kind of see how it works. I'm going to rotate the globe. The Earth turns around and it heats up one side, then it heats up the other. It gets cold, it gets hot, it gets cold, it gets hot. That's not a good thing. Okay, so another thing is global temperature. There's all these ocean currents that actually circulate the water around. Well, if the heat capacity were a lot lower in water, now what's going to happen is that it's going to be too hot or too cold just from year to year even. So, from summer to winter, I mean. So summer times would be a lot hotter, and winter times would be a lot colder. But because of the heat capacity, it will even things out. Also, because of the heat capacity, it can actually store heat in the tropics, and then when it goes up north where it's colder, it actually brings it to other parts of the planet. Okay, so it's like an evening out effect, okay, which is also a really good thing. It turns out water has the second highest heat capacity of all liquids and solids. So once again, it's a really, really good medium to use. Okay, talk about another one, heat of melting. And heat of melting and heat of freezing are actually the same thing. So the heat of melting is the amount of energy it takes to melt something. Heat of freezing is the amount of energy released during freezing. Those two numbers actually turn out to be the same thing. So, yeah, so it
Makes
yeah,
sense.
yeah,
Okay.
so you need a liquid. This is very similar concept. You want it so that you don't have drastic changes in the temperature on your planet. So you need a liquid that has a high heat of melting. For one reason, it keeps glaciers from melting. Al Gore would be happy, I guess. Keeps oceans and lakes from freezing. Regulates global temperatures. And water is the second highest of all liquids. Okay, so it has the highest heat of melting and heat of freezing. Yeah.
What's the first highest of this and the previous?
Ammonia.
Ammonia?
Yeah.
What about the Heat capacity, same difference? Is it still ammonia?
Yeah, heat capacity and heat of melting are both
Ammonia?
ammonia. Yeah, we're gonna get to ammonia in a minute too, by the way. Because, well, you'll find out. Okay, stay tuned. Heat of evaporation, there's another one. Once again, the amount of energy it takes to go from liquid to gas, okay? So you want it to be high to keep the oceans and lakes from getting too hot, okay? The oceans, as they get hotter, they start to the water starts to evaporate. Well, that helps cool it off. Okay, so you don't want the oceans boiling. You don't want them getting so high that now you have to do this whole design thing of trying to make your life work at 212 degrees and down at 32 degrees all at once. So you want it to be high. Well, water has the highest value of any known substance. Ta-da! Surprise, surprise, right? Okay, thermal conductivity. Here's another thermal property. Okay, so thermal conductivity is how quickly heat will spread out and distribute itself evenly. Well, you kind of know about electrical conductivity. It's how electricity can get through something. Well, same thing with thermal conductivity. It's how well heat can travel through a substance or within a substance. So you want it to be high, once again, to moderate global temperatures. Here's your lake. Oh, I know. Okay, here's your lake. Or ocean, maybe. Okay, so heat comes down, right? Heats it up. Water has the highest value of any liquid other than liquid metals. Turns out metals beat out water. So I guess you could try to come up with a metal-based life form. It's going to be liquid metal. Okay, so I got heat coming down. Ice, it turns out, is an insulator. Okay, there's another weird thing about water. When it turns into a solid, it's an insulator. Okay, so you got heat coming down like in the summertime. Well, you get ice in the wintertime. Well, what happens? I'm not sure if reflecting is the best way to say it, but the heat doesn't escape anymore in the wintertime. So it helps keep the lakes warm. So there's another feature. Heat comes out, same thing, water reflects. Okay, so the ice reflects it. Okay, so
That's like why Eskimos build igloos, to keep them warm, because the ice reflects the heat.
Yep, ice is that's a pretty good thing. I guess if you're an Eskimo anyway.
Well, that helps support life too.
Yeah. Okay, here's your ammonia, okay? All right, so back in the 60s, many people thought that life could be based on other substances. Ammonia was one of the most popular mentioned because this was something that was posted in 1963 in the New Yorker magazine. Some alien being crashes in the middle of the Sahara Desert. Instead of saying water, water, what do they say? Ammonia, ammonia. So anyway, so there's actually still websites dedicated to the idea of ammonia being the medium for life. So you can have ammonia-based life instead of water-based life, okay? So let's see here. So let's look at some of the properties. Okay, so here's the first three properties we already talked about. Heat capacity, heat of melting, and thermal conductivity. Well, they're all about the same between ammonia and water. But it turns out that ammonia beats out water just a little bit for heat capacity, and it beats out heat of melting. It beats out water just a little bit, and thermal conductivity is just a little bit less. So it's actually pretty close because they call it a thermal analog to water. Okay, but let's see here. Yeah, this is not real good. Heat of evaporation is only about half as much. The boiling point is minus 28 degrees Fahrenheit. Well, now you have to have a planet that is colder than minus 28 degrees Fahrenheit in order to have your life now, because you need something liquid, which we talked about before. That's why I covered the liquid before. And is it chemically stable? Well, ammonia is not very chemically stable, but water is. So now you get this whole problem of chemistry and all that kind of stuff coming into play. Okay, so let's see here. Hold on a second. Okay, so you need all these properties, you need all of these properties to support life, not just one, or not just some of them. If you're missing one, you can't get life anymore, yeah.
Now, chemically stable, is that like the 1 out of every 10 to the negative 7, or 10 to the, I forget how it is, 10 to the 14 water molecules, like disassociates into H and OH ions?
I don't think that's what they're talking about. I think they're talking about how much it combines with, put something in a glass of water and does it explode?
Oh.
You know, that kind of a thing, you know. Actually, ammonia, you gotta be careful with, right? You mix ammonia with something else and you can pass out. Seems like I remember my sister doing that once.
Bleach.
Bleach and ammonia.
Bleach, yeah, that's right, yeah.
It makes, actually makes what they call
Chlorine
hydrazine.
gas.
Yeah, so, okay.
Which is a rocket fuel.
Ah, yeah, so,
Wow.
and you want it to be stable.
Not,
Poor
Yeah.
man's rocket fuel.
Rocketry.
not in the
high school.
concentrations you can make in your car.
Right, but if you're gonna have something running through your veins, you probably don't want it to be too volatile, right? Okay, so, not shown here is what's called the dielectric constant of water, which is 4 times higher, making it a better solvent, making water a better solvent. Surface tension is something else that's important, which we don't have time to get into, but it's 1/3, ammonia is 1/3 of that of water. And hydrogen bonds that exist between ammonia molecules are much weaker than those of water. Hydrogen bonds we'll get into a little later. So, the other thing is expands and freezes. Ammonia doesn't expand and freezes, so you get another problem. So, I say it's good for science fiction movies only.
I've never seen that in a science fiction movie of a life form that has ammonia as a solvent. Where I've heard silicon-based life forms all
Yeah.
the time, but not.
It's because it's easier to explain silicon-based life forms than ammonia-based life forms. Because ammonia-based life forms mean you have to talk about that we're really a water-based life form. And so now you have to go through all this discussion. You don't want to do that in a movie.
And you wouldn't be able to have the 2 people in the same room because one would start evaporating.
Yeah.
Okay, deal with that.
That'd be a problem. Okay, so now we're going to talk about what I call the temperature problem. Okay? So, this is your brain.
Oh, really? Here we go.
This is your brain if it gets too hot. Okay, so it's something called denaturation. Okay, I don't know if I'm pronouncing it. Do you know if it's pronounced right? Denaturation? Okay. What happens is the proteins, if they get too hot, they actually denaturize, means they actually unfold. Actually, you might have actually gotten into this a little bit.
Denaturize, isn't it denature?
I don't know. Yeah. So they unfold, and sometimes, a lot of times, they don't fold back up again. So in other words, if you cool back down, they won't fold back up again. So it's kind of like a one-way street. Okay, not a good thing. So.
Oh, and all the protein folding, sorry, that's like a whole different presentation
Yeah,
of all the
whole
acids for
different
design.
thing. Right. Okay, so here's a cell. This is my rendition of a cell. I grabbed it off of something and clipped it. Okay. So here's a cell. It's got a little nucleus in there, a bunch of other stuff that you can't see. So let's say you have a cell. Chemical activity generates heat. If it gets too hot, what's going to happen? It's going to all the little proteins that are inside the cell, they're going to denature. Whatever. Okay. So yeah, they're going to unfold. Very good. So how do you prevent that? Well, the first thing is the heat capacity. Remember, water's got the second highest heat capacity. Well, what it can do is it can absorb all that heat, and it won't actually raise up in temperature until you really get a lot of heat. Okay. Let's see what else here. Now you have a bunch of cells around it. So now you're talking about a multicellular creature. Okay. Well, you got to get the heat out through all that. Well, another thing that would be very useful is if you could get the heat through some other means, and that's conduction. You can the heat will actually conduct out through the cell. Okay. Once again, it's the highest except liquid metals. Okay. Okay, so I'm going to continue with this idea now. Take it a step further to animals. Okay. The average man, we call man an animal for lack of a better word, he generates 2,400 calories a day. If there's no way to dissipate that heat, his temperature in that one day is going to rise 250 degrees, okay? Because he's big, he's a lot bigger than those few cells that I was showing you. It takes a lot to get all that energy out, okay? So heat capacity, we already talked about. Due to heat capacity alone, actually, now instead of 250 degrees, now it's only 90 degrees, okay? But still, 90 degrees hotter than your normal temperature is still life-threatening, right? Still a major problem. So how would the designer solve this problem? Well, this is what I thought of, is I would start to use pipes to circulate the heat around, right? Kind of a common thing you might do in a house or in a car or whatever, a computer, right? That's what I would do. So you're gonna pipe it through, circulate it through. Obviously I'm talking about veins and arteries and such, right? But I call it pipes, okay? So you got these pipes, well, what do you need to circulate it? You need a pump. You start to pump it, well, what's the property of the liquid that's gonna make it so it needs as little pumping as possible, as little pressure as possible? Viscosity. Okay, what's viscosity? Well, I think of it as, think of honey. Honey is very viscous, okay? It's resists the flow.
And
right?
glass, the silicates you're talking about earlier, right?
Yeah. Yep, glass, right. Tar, okay? You wouldn't want your blood vessels to be pumping tar. You know how big your heart would have to be in order to pump that tar through your body? Pretty big, okay? Okay, so let's see here. So, for viscosity, okay. So then I would say, well, that's good enough to circulate it, but let's get it from pipes out to the surface or the skin of the animal. Well, how am I going to do that? Well, I can't do any piping anymore because, you know, you can only you do so much with the piping. Well, now we talked about the conduction. Your blood vessels can get really close to your skin, but how does it get out from there? Well, it conducts just through this through the thermal conductivity. Okay. Let's see here. Did I say water has one of the lowest viscosities? Oh, I already talked about that, right? Okay. Oh, the other thing about the viscosity is also the pressure would have to be increased, which means now you have to make your blood vessels thicker to be able to withstand that pressure. So that's another thing. And the other thing about viscosity is if it's too low, it turns out that the cells would actually be disrupted by external shocks and stresses. So you don't want to have it too low either. Water's pretty low, but there are substances that could actually be lower than that. Okay. Okay, so let's see. So we got it from the pipes to the surface. Once you got it to the surface, now what are you going to do? Any ideas? What'd you do with What would you do with a computer, right? I think of computers because I've built a lot of computers. You have fans blowing on it, right? All this kind of stuff. Well, when I get from the surface to the environment, evaporation, right? So we already talked about the heat of evaporation, right? Well, there's more than one way to cool off your body. One is through our skin, sweating, right? But there's also sweating, there's panting, there's licking. I didn't realize this. Sometimes the cats lick themselves and not to get clean. Sometimes it's to cool themselves off. And splashing. So you got birds that go in the water and they splash around, right? We actually do swimming and stuff, right? So that actually cools people off, cools birds off, cools animals off. So water has the highest heat of evaporation of any known substance. And what I was going to say was it looks like when water was created, it knew all of its purposes ahead of time. Because there's a lot of things that it had to know about. Okay? All right, capillaries. Okay. Capillaries work by a process called diffusion. Okay? Diffusion relies on low viscosity. We're talking about viscosity, okay? Maybe I should have had one of those little cheat sheets like Fred had last month. But anyway, it's how quickly molecules spread out in the solvent. That's what diffusion is. So think if you have a tank of water, you drop ink in it, how fast does it distribute? It actually distributes fairly fast in water, but a tank of honey, not so fast. Okay? Let's see here. Why is that important? Well, oxygen takes only 1/100th of a second to go from one side of the cell to the other because it's water. Okay? It only works over small distances though. So you can't use this way of distributing oxygen or chemicals or whatever throughout your body. You can't use diffusion everywhere, but you can use it over very short distances, like in a cell, okay? So it's very important that you have this low viscosity, which means high diffusion rate for a cell. It turns out that it determines the maximum size of a cell, because you have to have the chemical, the oxygen, whatever, going from one side of the cell in a certain amount of time, otherwise something bad happens. You held your breath for a while, you get dizzy, all that kind of stuff, right? So it turns out that it's actually pretty sensitive to this. It says it turns out that if the viscosity were 100 times higher, which is what olive oil is, it would have the cells would have to be 1,000,000 times smaller. Well, 1,000,000 times smaller turns out that would only hold just a few proteins. Any idea how many proteins are in a cell? There's a lot of them. I don't know how many, but having just a few proteins, I don't think you can even get an organism out of that. I don't
The
remember
smallest bacterium is about 100.
100, yeah. So you need at least 100 proteins, and we can only get 2. So you can't use olive oil. So you see how sensitive things are to that. Okay. Okay. So let's see. It also determines the size of the capillaries. Once again, we were talking about before that if it's too viscous, you have to make the walls of the capillaries thicker. Turns out that the capillary walls, most of them in our body are only one cell thick. I didn't realize that. One cell. And the tube that the stuff runs through, the blood, you only put one blood cell through it at a time, apparently. I didn't realize that either. The capillaries, not the veins and arteries. Okay? So it's very fine tuned, okay? So if you increase the viscosity, it means you have to increase the pressure, means you have to increase the capillary walls, right? Because they're not going to be able to hold it. If you increase it by only 33%, the capillaries would need to take up 100% of the tissue. And that's quite a bit. Only 33%. Okay? So if it's any lower, you run into other problems like the cell structure not being stable, like we talked about before. So viscosity of water is actually fine-tuned.
Is that why high-fat diets are, like in the West, especially with all these weird fats, that they cause all these problems in people?
I have no idea.
Because the increased viscosity and
Do they talk about
disruption of
increase
the-
in viscosity?
of
No,
the,
I think they just
capillary.
reduce the area, which
They're
almost
changing
amounts to the same thing.
Oh, yeah, maybe.
They're changing the parameters of that.
Of
Design.
the capillary, or of the,
Yeah, so you have to push more, blood
I see. Okay,
for the same effect,
okay,
because it builds up on the walls, right, of the artery.
yeah. Okay, so we don't have enough time to go through all of the properties that are unique to water. That's about all of them. We might get into something else a little later, but there's just too many of them. So I just touched on a few, but there's a website from the London South Bank University. They actually have a website that lists 70 anomalous properties of water. 70. I think we talked about what?
What's it called?
London South Bank University. And Wally, did you pass out those sheets?
I was looking at it.
Is it on there?
Yep.
I was thinking of putting it on there. I can't remember if I decided if I did or not. Under resources, maybe?
Yeah, it's in the back.
Okay, it's the
70
last one.
anomalous properties of
Yeah,
water.
yeah. They spell anomalous without any vowels, I guess. So.
What does that say? Or is it- or is it-
It's there.
Yeah. Should be the last one.
On the back side, the last
Got
thing.
it.
Yeah.
Okay, so the other thing, I kind of wanted to pull things together a little bit here, and I called this coincidences. There's many coincidences in water, okay? And the coincidences I want to cover is, there's a whole bunch of them, but I just want to cover a couple here. It turns out that for many processes to take place successfully, you have to combine several of the properties of water together or whatever substance you choose, you have to combine many of these properties together in order to get something to happen. Let me just give you some examples here. The first one is weathering. So weathering and erosion, all that kind of stuff. It turns out, I don't have them listed here, but it turns out you need 6 properties to be fine-tuned in order to get it to work, in order to get weathering to work well. Similar to liquid water on the surface of the earth, you need 7 of these properties. Okay? Temperature regulation in your body, you need 4. And temperature regulation of the whole earth, actually I don't have that number, but we already talked about 4, I think, in previously. So the interesting thing is you just have to have all these things working together. You can't just pick and choose, well, and you have to have, what I'm trying to say is you have to have all of the properties in one substance. You can't just say, well, ammonia's got this one, and hydrochloric acid has this one, and this other one has this one, so that's good enough. No, it has to be in one substance. Okay? So because of that, it was enough to make a Nobel Prize winner say this. See if I can get it here. Water is the most extraordinary substance. Practically all its properties are anomalous, which enable life to use it as building material for its machinery. Life is water dancing to the tune of solids. So I thought that was a kind of an artistic quote that I decided to put in there. Now that was actually said by the discoverer of vitamin C back in 1937. So Michael Denton, he's a molecular geneticist, he says if water did not exist, it would have to be invented. So I've been working in the engineering field for 30 years now, and one of the things I've learned when you do a design is, I just kind of thought off the top of my head here, but there's 2 things that are really important when you do design. One is you have to understand your goal. You have to know where you're headed. The second is you have to optimize all the stuff to make it happen. There's a lot of optimization going on. When I did my work at the first company I worked for, you see cubicles of engineers pushing a button called optimize, and they go out and get a cup of coffee and come back again. Because optimization is just a really big thing. You want to make whatever it is you're designing optimize for your goal. Okay? That's what I found when I was reading about all these water properties. I see, gosh, it seems to have this common goal. And it seems to be optimized to that common goal. So I'm just going to talk a little bit about the abundance of water on planet Earth. Well, actually, just the abundance of water in general. It's pretty important that whatever molecule is used for all these things that we were talking about, that there's a lot of it. Water, it turns out, is the 3rd most abundant molecule in the universe, which we talked about. It turns out that it requires a particular type of universe in order to get that to happen. It turns out that if you read Hugh Ross's book on creating the cosmos, I think, he probably has several of these, several books that he's written about this, that the expansion rate of the universe, if it expands too fast or too slow, you don't even get atoms sometimes, depending on how fast or slow it gets. Or maybe you only get hydrogen. That's all you get. Well, you need oxygen, at least for water, right? So you need a fine-tuned universe, okay? Let's see here. Liquid water on the surface of a planet is actually very rare. The most obvious reason is you have to have the right temperature. If it's too hot, it's going to turn into gas. If it's too cold, it's going to freeze, turn into ice. Nearby planets here. These are the 2 nearest planets to Earth. One on the left is Venus. These are to scale. Venus is just a little bit smaller than Earth, actually. One on the right is Mars. It's about half the size of Earth. Turns out if you look at all the planets out there, there's a wide range of sizes.
Jupiter's huge, isn't it?
It's huge. Yeah, you can't even put it on the screen.
Wow.
You know, compared to Earth. Talk about Venus for a minute. Venus is Earth's twin. They call it Earth's twin because it's so similar in a lot of ways. It's actually, I think it's only 30% different in terms of the distance from the sun. So it's actually got a lot in common. But it doesn't have liquid water on the surface. I don't even know if it has liquid water, if it has water anywhere, I'm not really sure. But it used, at least they think, scientists think that it used to have water on the surface. But because of its thick atmosphere, it would overheat, and it just gets hotter and hotter, and then the water just turns into vapor and eventually goes off into space. Mars, they think it also started with liquid water, but its lack of atmosphere means the liquid water would just evaporate. Europa, you've probably heard people talk about Europa. Europa is a moon of Jupiter. A lot of people think there might be life on Europa somewhere. Well, turns out that Europa is actually 15% water. 15% the whole planet, not just the surface, okay? 15% water, but there's no liquid water on the surface. It's minus 260 degrees Fahrenheit on Europa. They think that there's 10 miles of ice before you get down to the liquid water. So there actually is liquid water in Europa, not on Europa, okay? They think it might be 50 miles of ocean underneath, okay? But you need liquid water on the surface in order to have life, because the surface is where you get the energy. The surface is where there's light. I'm pretty sure if you go down 10 miles under ice, you're probably pretty dark down there. You also have to have heat and all these other things. Energy. Okay, Earth. Earth has liquid water, believe it or not. 71% of Earth's surface is liquid water. So what are the requirements to retain liquid water on the surface of a planet? Well, you probably have actually heard of a habitable zone. You ever heard of that? Sometimes they call it the Goldilocks zone because it's got to be just the right place. Habitable zone means it's just the right distance from the sun. Now the habitable zone is different for different sized stars and all that, okay? So it's not a simple calculation. But for any given star, you can compute what's the distance from the sun that you need to be in order to have the habitable zone. There was also something called the continuously habitable zone, which means that over a long period of time that it is in the right area, because you have to have your planet you can't just have the planet be in this habitable zone for a short period of time. It's got to be a very long period of time, especially if you want to evolve a life form to something like humans, okay? I'm not saying that that's what happened. I'm just saying that that's if you go from a naturalistic point of view, that's what you have to do. Okay, what else? You have to have just the right atmosphere. Otherwise, the water would just evaporate into space. The planet has to have just the right mass. Gravity high enough to hold on to it, but low enough to let the light gases to escape. Earth's mass must be within a few percent to maintain water over a long period of time, without also retaining life-suffocating molecules such as ammonia and methane. You don't want to have a lot of ammonia or methane on your planet because then it's going to suffocate life. Okay, there's something else here. You have to have just the right solar system that has, this is our solar system. In the center is the sun. You got Mercury, then Venus and Earth and Mars, and Jupiter's like way out here, and then you get other planets out there. Well, inside here is this asteroid belt. And there's also some other asteroid belts in other places in our solar system. I think there's like 5 different asteroid belts. Well, it turns out that asteroid belts are necessary for life. Most solar systems have either a lot more or a lot less comets and asteroids. Well, why? What happens is that comets especially, they pummel the planets with ice, which brings water. And that's actually a very important thing to be able to do. It helps resupply the planet with water if it loses it. But you don't want too much, because if you got asteroids hitting your planet all the time, it's kind of hard to live. Probably kind of hard to live even if you're a little bacteria, especially if it's boiling your oceans or if it's upsetting things dramatically, tearing you apart, etc. Let's see here. Okay, so there's probably a lot more to this list, but I just put in 4 that I happen to come across. The other thing is you have to maintain these conditions over a long period of time. You can't just have it a short period of time, it's gotta be a long period of time. Okay, so total water in or on the planet. Okay, here's a quiz. What percentage of our planet is either ice, water, or water vapor? Give me a number.
Of the entire mass, or is this mass volume what?
I'm giving it away. I was gonna try to trick you, but he already figured it out. Okay, so it's gonna be a trick question. I was hoping somebody would say 71%. Yeah, okay, but it's not just the surface of the planet that counts, it's the whole planet you have to think about too. Turns out that our planet has, you wanna take a guess? If you take the whole volume of the planet,
Well, I don't know.
how much is water?
It depends on how much water there is in the like core and the mantle and.
They're estimating 0.02%. Pretty different than 70%, right? Okay, so,
Is that by volume or by mass?
I don't remember. Sorry. I don't remember. I might get to it here. Mass, it's mass. Yep, sorry, it's by mass. Okay, so, turns out more is not better when it comes to water. It's good to have water on your surface, not too much though, we'll get into that. But it turns out that you don't want your whole planet made of water either, that's not a good thing. There's actually a threshold where even the most aggressive plate tectonics won't produce continents. Well, you have to have continents to have life like us anyway, okay? No continents also means you have no shoreline for life. Shoreline, there's a heck of a lot of life on our shores, right? There's actually very little life at the bottom of the ocean compared to what's on the shores. The other thing is I happen to think about is if you had a planet completely, the whole surface was water, well, you can't have much technology now, can you? You can't even start out with, what's the very first invention you always hear people talk about? Fire. How do you get fire if you got a planet covered with water? I'm not exactly sure if that could ever be done.
Wheels.
Wheel seems kind of pointless too, yeah. Okay. Right. So, the other thing is if you have a lot of water, it turns out that makes it so you have a thick atmosphere. I'm not exactly sure why that is, but I read it so I believe it. A thick atmosphere blocks out light. If it blocks out light, then you don't get the energy onto your planet that you need. So it's definitely not optimal to have a lot of water. They've worked it out. They said your planet, the mass of your planet, if you're going to make a planet, it needs to have less than 0.05% water total. Okay? Earth is 0.02%. But Earth used to be, or they think, this is planetary models. They have planetary models that they think that Earth actually had 20% of the whole mass of Earth was water. Okay? They think that that's more normal for a planet our size, with our distance from the sun, all that kind of stuff. Okay? 20%, and now it's only 0.02%. That's a factor of 1,000. Something happened. Well, next month you can probably find out a lot more about this. Something happened. I'm going to give you a little bit of a precursor here. But remember, it's also not just liquid water, it's liquid solid gas. Okay, so it's total. Something called the Big Splash. There's all sorts of, Fred will know a lot more about this than I do, but I found one of the models that NASA has come up with, they call the Big Splash, where this planet, I guess you'd call it, long, long time ago, galaxy close by, hit Earth, and they call it Big Splash, splashed up more than just water. I mean, massive, massive cataclysmic event, okay? Well, something happened anyway. And we can learn more about that next month.
Quick question, is this the same event that formed the moon, or is this a separate event? Same
Well,
one?
depends on who you talk to,
Okay.
okay? But yeah, I'm pretty sure that's probably what most people
That's
would
a
say.
consensus view.
Yeah. I just wanted to read Genesis 1:2. Seems to say that Earth was originally a water world. The earth was without form and void, and darkness was over the face of the deep, and the Spirit of God was hovering over the face of the waters. I don't know if you really want to interpret that too strongly there, but it does make it sound like earth had a heck of a lot more water than it does now. Especially if you keep reading, then God did other things after that. You know, he separated the water from the land, all that kind of stuff. So what NASA is showing and what they're predicting actually matches what Genesis says. Okay, so let's see here.
Do you know? Does anyone know how Earth lost all that water? Would go from 20% to
Big
0.2%?
I think
Oh, the splash got rid of the water?
Yeah.
Okay,
Yeah.
so it's not the big splash splashing the water onto the Earth. It's
No.
the big splash
You
splashing
think
water
about
off.
it, like, the thing that hit Earth, at least one of the models, it's the size of Mars.
Alright, and that would like boil off the water.
It would boil it off. It would do all
Okay.
sorts of nasty things. Yeah, 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 yeah. There's actually, you go online, go to NASA's website. They actually have models. They actually show you little particles flying around and stuff. They kind of show you what they think happened.
They've actually done models where they've shot representative sizes of objects, one at the other, to simulate what they
Yeah.
think might happen back then.
Okay, so the other thing is that that this Mars-sized planet hits this. It could have actually stripped away too much water. I mean, we're only talking about 0.02% to 0.05%. I mean, went all the way from 20 down to point. I mean, that's a factor of 1,000. What happens if it's a factor of 1,500 or 2,000 or whatever? Okay, could have taken away too much. So it's just basically it's just right, just the right amount. The other thing is just the right amount of liquid water. Sorry, oceans to land, oceans to continents. There's been studies done about what's the optimum ocean to continent ratio. Well, we got it. It's interesting. Okay, so explanation. We've established that water has a lot of unique properties, all for the benefit of life. But do we have an explanation for that? Do scientists come up with an explanation of how all these things can happen with just one molecule? Well, they've come up with a little bit of an explanation. They've got some. They do know that some of the chemical properties of water and how the atoms are arranged and stuff actually does explain some of this. Who knows the chemical formula for water?
H2O.
H2O, right, okay. So, is that it? We got two H's and one O. Okay? Well, it turns out that's not exactly what water looks like, though. But the middle, basically I'm drawing here an oxygen with those little dots, they're electrons. This is a very simplistic view, okay? It's not really what's going on inside, but it's an artist rendition for entertainment purposes only, okay? But this is what most scientists, at least from a simplistic point of view, scientists would agree with this and they would draw it this way, okay? But there's a lot more going on than what I'm showing, okay? So you got two electrons up on top. You got two shared electrons. The hydrogen has one electron. The oxygen has 6. The oxygen shares one electron with the left hydrogen, one electron with the right hydrogen. Forms what's called a covalent bond. Very strong bond, okay? It takes a lot to break the oxygen or the hydrogens off of the oxygen. Okay? It takes a lot of energy to do that. It can be done though. So these two top electrons, the 4 electrons there, they're called lone pairs because they have no electron to share with, so they're lonely, I guess. Let's see here. Hold on. Make sure. Right. Okay. So the next thing is that those lone pairs up there, they're the 6 electrons that are around the oxygen. They are all the same polarity, right? They're all negative charge. Everybody knows electrons are negative. Well, negative charges do what? Do they attract or do they repel? They're the same. They repel. Okay. So what happens is the hydrogens move down because the electrons move down. Okay. There's actually a little more to it than that, but this is my simplistic way to put it. And by the way, the electrons don't actually just sit there like I got drawn there. Okay. They go around the atom and all that, the atoms and all that kind of stuff. Okay. So it turns out that water is actually bent. It's got this funny shape to it, and that's what I wanted to show here. Just another rendition of it. So you can pull this apart, just so you can kind of see. This is my little water molecule thing. So it kind of looks like Mickey Mouse. Okay, that's what it looks like. It's kind of like a 3D view. Now I've got these little purple things sticking off of here, which we're going to talk about in a minute. Those are called hydrogen bonds, because they attach to hydrogen, and there'll be another hydrogen over here. So anyway, so there's our Mickey Mouse there. I'll do my clipper. Here it is. So let's see here. Turns out that the angle is actually important. It's 104.5 degrees. Somehow that's actually important to something we'll get to in a minute here. It turns out that without this bending of the molecule, many of water's special properties would be lost. Okay, so we said water is bent. I'm kind of starting over here with a simpler picture here. It turns out that there's a tug of war for these electrons. Remember we said they were sharing the electrons? Well, they don't share them equally. The oxygen, because it's a little bigger, it actually holds on to the electrons a little bit more than the hydrogens do. Okay? Well, what's the effect of that? The effect is that the oxygen, they use these little Greek symbols, don't worry about that. Look at the minus sign next to the symbol, that's a delta. It's a little negative there, and these are pluses. Well, it makes it so that oxygen, because it's greedy and it holds on to the electron a little bit more, it makes it so it's a little bit negative. The hydrogens hold on to it a little bit less, so it makes them a little bit positive. Okay? What happens is that makes it so that it's what we call, it's polarized. The molecule is polarized. Because if you were to think if you're another atom or another molecule sitting up on top, and it's looking down on this, it's going to actually see more of the negative part than it's going to see the positive part, right? Looking down this way, you're going to see more positive part than the negative part. If these were not bent, and they were back up where we said before, looking down here, far enough away anyway, they would look about the same, so you wouldn't see that polarity. So the fact that water is bent, that's my term, I don't know if that's a scientific term or not, but the fact that it's bent is what makes it polarized, okay? All right. If it weren't bent, it would not be polarized. Okay, so now we're going to get to hydrogen bonding, okay? We talked about that a little while earlier. Hold on a second. Lost my page. Did I miss something here? Hold on. Oh, I did. I skipped a page. Okay. Before we get into hydrogen bonding, sorry. Water is more polar than all but one other molecule, and that's hydrogen fluoride. Okay? Because it's polar, explains why it can dissolve things better. Well, many molecules are slightly polar. And that's what I've got drawn here on the left. It's just think of it as some random molecule, maybe a protein, maybe a, whatever. If it has just a little bit of polarity to it, then what happens is that the red guys, those are oxygens, they're negative. They kind of attract, they kind of get sucked up into the positive side, and then the hydrogens on the other side, they get sucked up to the negative side, because positive and negative, opposite charges attract. So they can surround a molecule. That's what we would call, it dissolves the molecule. So because it's surrounding it, it dissolves it. The thing on the right here is actually a sodium ion, table salt. Anybody know what table salt, what the chemical formula is for it?
NaCl.
Yes, NaCl, sodium chloride. Okay, this is a sodium ion. Turns out that I don't understand all this myself, but you've heard about salt. You dissolve it in water. It actually ionizes, so you get dissociate. Is that the right word? Yeah, thank you. So you get positives and negatives. They're much more positive and negatives than these guys. So what happens is water can surround it. So that's why salt can get dissolved in water, because water is polar and because water is bent. Okay. And by the way, I guess I said, so water has this unique property that it's the second most polar molecule of all molecules. Okay, so next is hydrogen bonding, sorry. Okay, so because of polarity and because of those extra electrons, those lone pairs, water can form what's called a hydrogen bond, okay? Turns out that it's not a very good name for what it is, because it only partially involves hydrogen, and a lot of chemists say it's not even a bond. But we'll call it hydrogen bond because that's what they call it. It's actually a very weak bond. It's nowhere near as strong as those covalent bonds we talked about before that holds the hydrogen to the oxygen, okay? So, but it explains why water is sorry, let me, hold on. So it's a weak bond, but it helps, I want to say it helps water stick to itself. So it turns out that the positive of the hydrogen and the negative electrons of the oxygen, they attract each other. So it makes them stick. It makes water stick to itself. So it's very cohesive, I think is the word. Okay. So it explains why water is a liquid instead of a gas at moderate temperatures when it shouldn't be. It turns out that if it didn't have this property, water would boil at some. Oh, thank you. It's right there. Mine is 148
Wow.
degrees. Yeah, I knew I had it somewhere. Right. Okay. So don't worry about the donor, acceptor, and all that kind of stuff. Just look at the basic concept. It turns out that these have to be in line with each other too, in order to form a bond. Okay. So let's see here. What I'm going to do is, hopefully, if this works, I'm going to show you a video from the Canadian Museum of Nature. Okay, I got this online. It shows you how hydrogen bonds look, I guess. This is all artist rendition again, of course, okay? But the idea is that, go back, started there we go. All right. So it's got these little laser beams, kind of like Luke Skywalker, okay? As it gets close, they cling to each other. And as they get farther away, the bond disappears again. They get close. Okay, so this is what holds them together. This is liquid water, okay? They're holding them together, but they're not super strongly held together. So they kind of go in and out. Sometimes it's a good bond, sometimes the bond goes away. That's why liquid water holds itself together so well and it doesn't boil until you get all the way up to 212 degrees.
Oh, sorry. Is this why water has such a high surface tension? Or no? Is that different?
Yes, yes, it is.
It is?
Yes. Hydrogen bonding actually explains a ton of stuff with water. Okay. Okay, so it explains why ice floats, which I'll get to in a minute, and it's also, well, actually, let me just show you right now. Okay, so what did I do with my little Mickey Mouse here? Okay, so these are the hydrogen bonds, and what I'm going to do is kind of hold this up here. This is an ice molecule, okay? So all these purple things, okay, so you see the water, that's the little Mickey Mouses, okay? But they're connected together with little purple things. Those purple things are the hydrogen bonds, okay? When ice or water gets really cold, what happens is that there's not enough energy to keep, these don't move around as much. So the hydrogen bonds are constant, and now they're not breaking apart all the time. So they form a rigid connection. Well, look how far apart the water molecules are. Let me just take one of these and just look how much space there is in there, okay? Well, so it's taking up a lot more space than if I had two of these sitting next to each other like this, okay? So it takes up more space. That means it's less dense, which is why it floats. So you got a bunch of these guys really close together. I don't have enough of them to show you, but a bunch of these guys really close together versus one of these where they're really far apart. This takes up more space. This is really heavy, so ice is going to go up, the water is going to go down. Okay, so that explains why ice floats. I think it's fascinating. So the next time you're at a bar, because all Christians go to bars, and you have some
Juice bars.
juice bars, yes, and you want to witness to your non-believing neighbor, you can talk about ice floating and how that was designed by God. Okay? All right, so it turns out that the properties of water are very, very sensitive to these hydrogen bonds and how strong they are. It turns out that if they were just 5% weaker, that means that carbon dioxide would be 70% less soluble in water. So no Coke, no Pepsi, sorry.
What would happen to the carbon dioxide that your cells generate if it couldn't dissolve in water as efficiently?
Is carbon dioxide the thing that you get the bends on? Can't remember.
That's
No, that's
nitrogen.
nitrogen. Yeah. So,
You
but
get carbon
nitrogen has the
dioxide
same problem.
poisoning,
Yeah,
but I don't know, because that's when too
I
much
don't-
carbon dioxide is dissolving in your
I don't want to try it.
bloodstream.
Let's
All
try
right.
this at home.
The temperature of maximum density, let's see if this makes sense. Okay, so it turns out that the hydrogen bonds were 2% weaker, you wouldn't get this ice floating phenomenon. Okay, 2%. Water would not be liquid on the surface of the Earth at its average temperature if the hydrogen bonds were as little changed as if they were 7% stronger and 29% weaker. It also explains the water bridge that we saw in the very beginning. Partially, they found that only molecules that have hydrogen bonds will make a water bridge, or will make a liquid bridge. You know, basically it's defying gravity, right? By you have this bridge going across. They actually have taken X-ray images of it, movie images of it, to try to figure out why it does what it does. And they were actually just 2012, I think it was. They actually discovered something else about it they didn't realize. It turns out that just the outside portion of it is actually doing anything special. The inside is just there. You know, all the traveling, I guess, is happening like on the outside part, I guess. I don't know. It's just pretty interesting stuff. But they don't understand it that well yet, so I don't want to say too much about it because I'm probably wrong.
What does that mean? That means that if you cross an ice bridge, the rest of it might as well be hollow, only the little tiny outer portion is needed to support your weight?
I don't think so.
Okay.
Were you here for the water bridge in the beginning?
No, I came in like
Oh,
a few
you
minutes
missed
late,
it.
right before
Okay.
your big
Okay.
intro slide.
All right, so basically it was just 2 beakers of water with you know, separated by a certain distance, and as you pull them apart, there'd be water going across it. You can get it a certain distance apart before it breaks apart. And what they do is they put electrodes in to charge the water, and then so the one thing they were thinking was that the outside of the water was the water was polarized, but I think it turns out just the outside of the water is polarized. They said it was a total surprise to them. They did not expect that at all. Okay, so
Wait, what does that even mean? I still don't understand. Only the outside of the water is polarized?
the bridge, you get a bridge, it's like a tube,
Okay.
okay? Sorry, what I meant by another term,
I'll ask you about it
polarized.
after
Okay.
the...
Polarized means they're all pointed in the same direction, is what I meant.
Okay.
There's I'm using the word 2 different ways.
Oh, okay, I
So it was
see.
my fault, right. All polarized in the same direction, I should have said.
Okay.
Okay, so understanding, let's take it one more level of understanding, okay? We understand hydrogen bonds. So do scientists understand what causes hydrogen bonding? Well, the history is that in let's see if I have this here. Yeah, in the 1920s and the following years, they worked out the equations for the amount of attraction you should get between 2 molecules. And guess what? It's exactly what we see. 1920s, we figured it out. Great, right? Well, think of 1985. Something that was actually around since the 1920s called quantum theory. Well, one of the outcomes of quantum theory is that molecules, I'll call it, they get fuzzier, okay? They vibrate. They're fuzzier than how we draw them. They're kind of vibrating molecules. I'm kind of simplifying here. I don't really understand it myself completely, but it's probably a good analogy to say that they vibrate or they're fuzzy. Well, it turns out that upsets this classical model. And so by 1985, when they incorporated the quantum mechanics equations into the equations for hydrogen bonding, guess what happened? Bad news. wasn't right anymore. So their calculations didn't predict what we actually measured. I said, well, that's not fair. Maybe we should go back and ignore quantum mechanics. Well, you can't, right? Turns out that the fluctuating distances between the molecules actually weakens the hydrogen bond. So I put a little negative sign up here to indicate that we found an effect that actually weakens the bond between the molecules. It's a quantum effect, and the negative means that it makes it weaker, okay? Well, that's not good news, but then a couple decades later, around 2009 or so, they discovered another effect. Totally different effect, fluctuating distance between the atoms inside the molecule. And the angle, remember that 104.5 degrees? The angle, those are also fuzzy, okay? Well, that turns out that it makes it more polar, more polarized, because it changes the angle. Remember we talked about before how the angle actually makes a difference to how polarized it is? It makes it a stronger bond. Well, guess what? The two competing quantum processes balance one another out. So you're back to the classical model again.
Just with a bigger explanation.
With a bigger explanation, right?
Got it.
So, the point here is, and this is what kind of got me interested in this, was you have two physical phenomena that are extremely complex, that are designed to cancel each other out. Okay, so, what do people say about this? Thomas Markland, professor of chemistry at Stanford University, says, water fortuitously has two quantum effects which cancel each other out. Lisa Grossman from she's a science journalist at newscientist.com. She says, water's life-giving properties exist on a knife edge. But when I see things like fortuitous, I think of biblical terms. I think of providence. And these are, as far as I know, these are not Christians saying these things. Okay. Trying to hurry along here. So that's it for the science part of it. But I want to talk a little bit about the repercussions of this from a theological point of view, a philosophical point of view. One of the things I wanted to point out was that there's many different reasons to believe in the God of the Bible. But let me just show you. Here's a bunch of reasons. Hopefully you can read them. They're a little late here. There's the cosmological argument, the moral argument, the teleological argument, the historical argument, the existence argument, the mathematical argument, intentionality argument, probably all sorts of other arguments to argue for the existence of God. Quiz time, which one of these is what we've been talking about today?
Teleological.
Teleological. Good, from our philosopher back there. Thank you very much. Okay, so this is what the definitions are, if you care to read them. But the teleological argument is the fine-tuning design of the universe. It was fine-tuned or designed for intelligent life. That's the teleological argument, sometimes called the design argument. The reason why I put this up is because I want to make sure people realize that this isn't like the only argument we have. And the other thing is, to tell you the truth, the water argument of design is probably a lot less strong than, there's probably a lot of other arguments that are a lot stronger. There's all sorts of cosmology arguments for design, which you can actually put numbers to. I didn't put any numbers to. What's the probability that water would be like this? I don't know. Okay.
But see, water bridges the gulf between the physics arguments for intelligent design and the biological
Yes.
arguments for intelligent
You got
design.
it.
That's
Yes.
what makes the water thing so powerful. This is the
Yeah.
reason I came to this specific talk. Yeah.
Very good. Yes. And this is the thing I noticed was you usually hear these arguments for design. The universe is designed. The Big Bang was designed. You also hear this design about maybe the origin of life, or you hear about the Just life itself is designed, and protein molecules, all that stuff. This is kind of in between. So that's kind of neat, you know. By the way, there's a lot more of those that are in between too. I've actually come across them, and I'm thinking maybe these are more talks we might want to do at some point. Okay, so design is in more than just just chemicals like water. Design is in planets, in our solar system. There's design in our galaxy and the universe. So I just want to get you the bigger picture here. This is just one of the many arguments that you could use. One thing we do try to do when we reason for the existence of God is we try to use what's called the inference to the best explanation. We don't try to look at the different hypotheses that are out there and say what makes the most sense. So what we like to say is God is the best reason for, the best explanation for fill in the blank. Okay?
What's the most consistent model?
What's the most consistent with all facts?
With all
right? Yeah. Okay, so what explanations are given for design? I'm getting a little bit into theology or philosophy right now. Well, the Stanford Encyclopedia of Philosophy says they've actually classified the explanations into 3 categories. We have chance, we have physical necessity, and we have design. That's the 3, I guess we say, instead of explanations for design, maybe I should say explanations for the appearance of design. Okay? You see something that looks designed, sometimes it's not designed, sometimes it is. Okay? Just because it looks like it's designed doesn't mean it's designed. You have to think about it a little bit, right? So, let's see here. So I say my English isn't right here. Okay, so I should say that concept, these 3 explanations for design, they're true. Those are the 3 explanations you get for any kind of design, any kind of alleged design of the universe, or even when working a crime scene. Because crime scene, you're trying to figure out, is there design in the crime scene, right? Is there a human intelligent cause behind it? So let's see. So chance is the first one. Chance means we explain things as chance when they're low probability, but they don't exhibit some discernible pattern. Let me just give you an example. If I win the lottery, we might attribute that to chance, right? Somebody's got to win.
No, you have to go right back to that same store where we had.
Yeah, right. Yeah. Okay, so let's say I spin the roulette wheel, or if I roll the dice. If you bet on green 16 and it comes up, well, that would be just chance, right? Nobody would actually say that was design. There wasn't intelligent cause behind that. Somebody has to win it once in a while. But we only have one universe to work with. So we're not like spinning it lots of times or rolling the dice lots of times. So it's kind of hard to make that connection there and call it chance. We only spin the wheel once. Right now, assuming there are less than a gazillion universes anyway, because some people think there's a gazillion. I use the term gazillion, meaning a large number. But I don't want to put a number to it because there usually isn't a number that will describe it anyway. So if there were a gazillion universes, then you actually might be able to say chance could explain this. Got a gazillion universes? Well, one of them's got to have life, right? Okay, so aside from that, chance doesn't really explain it. Physical necessity is the other one. That means it has to be that way. There's physical laws that will explain it. Here's an example. Roulette wheel. I have a hard time saying that word. Roulette wheel. If the marble falls on the same number, the same color, every single time, do it again, green 16. Do it again, green 16. Do it again, green 16. Well, maybe it's not chance anymore. And probably not some intelligent cause per se. Maybe it's more that's just how there's a defect in the wheel or something, right? It has to be that way. It's made that way. Saying that the universe has to be that way due to some law is contrary to the present scientific evidence. There's no evidence at all that says that. Here's a couple of quotes that kind of show that. Stephen Hawking, most people know him. Some people call him the smartest person in the world right now. Certainly a pretty darn smart scientist. He says string theory allows a vast landscape of possible universes. And Paul Davies, another physicist, says the physical universe does not have to be the way it is. It could have been otherwise. So physical necessity is kind of out, okay? So what if I bet on a different number of that wheel? Yeah. What if I bet a different number every single time and I won every single time? Green 16, I get green 16. Do it again. Red 32, red 32. Keep doing it. I keep winning more and more money. Would you say that was chance? Probably not. Would you say that it was physical necessity? Is there a law? Probably not. What would you suspect?
You tampered with it.
What's that?
That you tampered with
I
it.
tampered with it, or I cheated or something, right? Intelligent design, right? There's some intelligence behind this, some design, okay?
This is remarkably like Lewis when he talks about arguments for God, and he says that Jesus must be either a liar, a lunatic, or a Lord.
Eliminate the two, yeah. Sherlock Holmes has something to say about that too, right?
Yeah.
I forget what the quote is, but something about if
Once you eliminate the impossible, then whatever
No,
remains, however
improbable.
improbable,
Yeah.
must be the truth.
Yeah. Okay, so let's see here. We're almost done. Design criteria. How do we detect design? Well, I don't know if you guys have ever read anything from William Dembski. He's a pretty difficult guy to read. Mathematician. He's done a lot of work on design. There's also whole groups out there that study how do you detect design. He came up with 2 criteria that if you only have one, it isn't design. Complexity is one. Complexity or low probability. Here's an example. The bridge, this bridge, I call it a bridge, that's pretty complex. You know, you look at it, there's lots of little pieces to it and everything, right? But, you know, it's a low probability that if you shook up all the earth that it would come out like that, right? So it's kind of a low probability to come out like that. Exactly like that. So that's complex, but you wouldn't call it design. Functional significance. Now there's lots of words for this. There's functional target, functionally significant outcome. Dembski calls it specification. What it means is there's a match to a pattern that we know independently. Or there's a goal or objective. The key is that it's this independent. Goal or objective or pattern needs to be detectable outside of the physical boundaries of the rule, of this roulette wheel that we're talking about. Here's an example. This is a blow up of salt crystals. Salt. Does people know salt is actually a cube? Okay. Well, I look at that, and that's what he would call functionally significant or it's specified, meaning that it actually matches a pattern outside of the salt itself. I have in my brain an idea of a cube already. I've seen cubes in other places. So I look at that and say, that's something significant. That has meaning, or might even have purpose, okay? But complexity, this guy over here, it has no functional significance. There's no meaning to it, okay? This guy over here is not, it has no complexity to it. It's just a cube. It's very simple. So neither one of those you would say were designed, okay? However, that you might call designed. Intelligent design, right? You would not expect that out of randomness, right? It wouldn't be chance, and it wouldn't be, what was the other one? Lost it. Physical necessity. It's intelligent design. Let's see, I think I got another one here.
Oh,
Yeah.
wait, what about the, when people see things formed in clouds?
Yeah. Well, okay, here's another one. This we didn't think was designed because it didn't match anything we already knew about. This, however, has a purpose. It looks like something we already know. So we have ways of detecting design. It's not like it's not a science here, okay? So look at water. Water has lots of unique properties. That's the complexity. It has a lot of complex properties, and it has this benefit that's independent of water itself. It has a purpose. They all work together to aid life. Okay? So therefore, we conclude that it's design. Okay?
Interesting choice.
Do we have time to go through some objections here? What do you think? All right. Well, all right. Let me just go through these really quick. There are. It's good to talk about the objections to your case. One of the things that when at work, what we try to do when we pose an idea, you try to throw darts at it. Other people throw darts at it. Let's throw some darts at the idea of design. Okay. What do people say against design? When they see something that looks designed, what do they say is wrong with us saying that it's designed? What's their objections to it? Well, one is evolution. They'd say life took advantage of the water. You know, the problem is that water was around before life was around, and it was designed for life before life ever came around. Even NASA uses the phrase "follow the water," right? They don't say "follow the ammonia." Okay, there's God of the gaps. That means I don't know how it was done, so it must be God. Okay, sometimes that's actually a valid complaint or a valid objection. Valid use is like saying, I don't know how something happened, so you must be cheating. Well, that might actually be a valid reason. I don't know how you did it, and I see all these other things, so cheating seems to fit in pretty well with that. Okay. But most people would conclude when I did that thing about the betting and really doing the wheel, most people would conclude that I was cheating. That's because it matches both of those design criteria. Okay, so another one is "but we're here." That's what I call it. I haven't actually seen it called that anywhere else, but that's what I call it. It's sometimes called the anthropic principle. We actually got that a month ago. Somebody was saying that. I don't know if you remember that or not, Fred. I've actually come across it a couple of times. What that says is that it says, what do I say? This is what the argument is. Given the fact that we're here and we're alive, we should expect to observe a life-permitting universe. Because we're here, we can observe it. So we would expect it to be life-permitting, right? On the surface, that actually sounds like a kind of a good argument. Well, not according to most philosophers, though. It turns out that that's an argument that I've never heard a philosopher use, someone who's actually studied it. I only hear scientists use it. Scientists use this quite a bit. What's his face? Lawrence Krauss has used it. Richard Dawkins has used it. They're scientists. I don't know.
It's something like, I know this is completely improbable, but here we are.
Here we are, so that explains it.
A circular.
But see, that doesn't give you the specific explanation.
Yeah.
That just means that there is an explanation out there, not that therefore it's a, this type of explanation.
So here's a way to think about this. Say you're in a firing squad, sorry. There's a firing squad, 100 marksmen are gonna shoot at you. You hear the bang, 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 bang. I'm still alive, okay? So you say, I see the reason why I'm alive. It's because I'm here. That explains it. I don't think too many people would say that, right? Well, it's almost the same idea of the universe is so fine-tuned. It's so fine-tuned, it's because I'm here. It's almost the same argument. Okay, so they're basically saying, I see the reason why I'm here. It's because I'm here. Doesn't make a lot of sense when you put it that way. Okay, the other thing I was going to say is that I'm not exactly sure how something that happens in the present can actually be the explanation for something that happened in the past. Right? So right? How can me being here now explain something that already happened?
Can I point out something that I learned by browsing Wikipedia, that this type of argument is common all over the place, and people use it all over the place in different types of arguments.
They do?
And it's called a thought-terminating cliche.
Thought-terminating cliche.
Yeah, look it up on Wikipedia, anyone who wants to learn more about that.
Stanford Encyclopedia of Philosophy says, while trivially true, the anthropic principle has no explanatory power and does not constitute a substantive alternative explanation. So I have somebody to back me up here. Another one, I pushed the button you said not to push. What do I do?
I don't know. Touch it and push it.
All right, here we go.
And this talk is over, thank you very much.
Yeah, I know bad things happen.
Wow.
You'll have to go through the whole thing.
Okay, you're right. Screen it black. Really?
No, just go to the.
Oh.
Oh.
I didn't do it.
We're here.
Okay. Okay. Another one is who created God? Basically, it's if you're saying that God designed and created the universe, then who created God? It's an argument I've heard. Well, that's a category area because God doesn't need a creator. He's not something that was created, so he doesn't need a creator. There's actually a lot of things to say about that one. Stonehenge. Would you say, basically what they're saying is who created God? If you don't, one of the arguments is, or against this is, if you don't know who created the creator, that must be it's not true. He could have created it because you don't know something about him. You don't know who created him, so therefore he couldn't have created the world. Okay? Stonehenge, we don't know who created it. So is it valid to say it wasn't designed or it wasn't created by an intelligence because we don't know who created it?
Or even that it doesn't exist, I mean.
Or it doesn't exist, maybe.
Yeah,
Yeah,
you could
yeah.
even say, well, I don't know who created God, so God doesn't exist.
That's true, you could do that. Arrowhead, oftentimes we don't know anything about the people that made the arrowhead, but we still say they're designed. We don't know, maybe using somebody else's argument, you might have said that we don't know who created the thing that created the arrowhead, but we still think it's created.
The notion, this very childish question, who created God,
Yeah,
points towards any God who is in need of creation is a pretty weak God. And that's not the one we're talking about.
that's not the one we're talking about, that's right,
Yeah.
that's right.
Not
Right. There's also the many worlds hypothesis. It's also known as multiverse, like universe but multiverse. Okay. Remember I said before that chance can't explain the universe unless you have a gazillion universes. There are a gazillion universes. One of them is going to have life in it, right? Well, there's actually, I didn't realize this. William Lane Craig actually has some really good arguments against why the multiverse or the many worlds hypothesis doesn't explain design.
But he even would say, well, let's grant you that, even if there were that, it's
Even
still
if there were,
decide.
which we don't know if there are, okay? I'm not saying there's multiverse or multiple worlds, but if there were,
Yeah.
and this is a current theory, it's been around for about, you've heard about it, probably the past 10, 15 years or so, it's become a big thing. So, let's see here.
I like Ross's to take on the multiverse that's saying, well, if you flip a coin a million times and it always comes up heads, then the explanation that you're giving is, well, see, there exist a million other rooms,
Right.
all with a million
Yes.
other people flipping
That's-
a million other
that's
coins,
called the-
and they're all
yeah.
getting different results.
That's
And
called,
that's why.
that's called the gambler's fallacy, I
Yeah.
think, right?
And
So
we
are
have
you
no
gonna bet
evidence
on
for
it
any of
happening
that.
again?
We have no
Yeah.
evidence for any of that.
Yeah.
It's a
We have no
So-
physical evidence of any universe of our own, so.
Let me read what William Lane Craig says. He goes, or again, if our universe is but one member of a multiverse, then we ought to be observing highly extraordinary events, like horses popping into and out of existence by random collisions, or perpetual motion machines, since these are vastly more probable than all of nature's constants and quantities falling by chance into the virtually infinitesimal life-permitting range. That's pretty interesting.
William Susskind, I might be misunderstanding his explanation, but I think that's William Susskind's theory of multiverse creation, that constantly within our physical universe there are new universes being created as it expands, and basically new things popping in and out of existence, and that's why I'm thinking
Right. What
about
it's saying is that popping in and out of existence of horses is actually more likely than having a the fine-tuned universe that we have. And the other question would be, why aren't we living in a only slightly fine-tuned universe? There's a lot more, if you take those gazillion universes, there's a lot more slightly fine-tuned fine-tuned universes than very fine-tuned universes. Why aren't we living in one of those? Okay, so just to summarize here, we've looked at design at all levels. We've looked from the solar system to the planet, to specifics on the planet, to the organism, to the organ, to the cell, all the way to the molecular and atomic level, and even the fundamental forces of nature. The design shows purpose and is optimized, which matches my own experience as an engineer. It shows purpose and it's optimized. And it seems to me like design is the best explanation. Here's a quote from Hugh Ross, the founder of Reasons to Believe. He says, to explain everything that we observe, there must exist a causal agent beyond the universe that is living